Hi folks, we're going to take a look at questions 10 and 13 on page 241, and since they use similar tricks, I'll do them both together. So let's take a look at this first one here, which in fact is just one of our Pythagorean identities. So I notice here that I'm working with cosecant and cotangent. I'm choosing to start with the right-hand side. I just think there's a little more I can do here. And one thing that we often do is, because we're used to working with sine and cosine, that we often will turn these types of trig expressions into expressions using sine and cosine. All right, and that's what I'm going to do here. So with my right-hand side, instead of writing this as cotangent squared x, I'm going to write it as cos squared over sine squared, okay? Just the reciprocal, essentially, of tangent. All right, so let's start with that. 1 plus cos squared x over sine squared x. And so now what I have is I have the opportunity to add these two expressions using a common denominator. All right, so let's see what happens here. So this does not have a distant denominator of sine squared, so I need to multiply numerator by sine squared. So I've got sine squared x. Then this one here already has the denominator of sine squared, so I don't have to manipulate the numerator. So cos squared x all over the common denominator of sine squared x. Okay, and hopefully here you realize that something very nice happens in the numerator, because sine squared x plus cos squared x is just equal to 1. All right. And of course here, if you want, you can think of this as 1 over sine x all squared. And of course, 1 over sine x is just equal to cosecant x. So this can be written as cosecant squared x, which is exactly equal to my left-hand side. Okay, so we've proved that identity. And so now if we move on to the other one, I'm going to do something similar. I'm going to take what I think seems to be the more opportune side, which is again the right-hand side, and I'm going to write everything in terms of sine and cosine. Okay, I'm also encouraged by the fact that there's this cosine in the denominator. So let's do that here. So we've got sine x over cos x plus cos x over sine x. And now, yet again, we can add these with a common denominator. So this time our common denominator is going to have to be sine x cos x. So here I'm missing a sine x in this denominator, so I need to multiply it to the numerator. So that's just going to become sine squared x. Okay, here I'm missing the cos x in the denominator, so I'm going to multiply that numerator by another cos x, so cos squared x, and I think you can see what's going to happen there. And then my common denominator is sine x times cos x. And so yet again, this numerator just ends up being equal to 1. Okay. Now I notice that I'm going to want a cos x in the denominator, so I'm not going to manipulate that one. So I'll just write this here as 1 over sine x times 1 over cos x. And of course here, we know that 1 over sine is equal to cosecant. Okay, so we've got cosecant of x times 1 over cos x is just going to be, oh, sorry, that should be cosecant. Sorry about that, over cos x. And there we have it. There's our left-hand side. Okay, so just to recap here, when you're working with secants, cosecants, cotangents, or even tangents, it's often useful to just turn everything into sines and cosines. It's just easier to think of ways to manipulate those more common trig ratios. Okay, that's it for this one.